session of this first PRIMA meeting. It's my pleasure to introduce to you Stanislav Smirnov. Stas has made many contributions in the field of mathematical physics and statistical mechanics. One that he's most famous for, which work he did in 2001, in which he was the first one to prove rigorously the conformal invariance of a two-dimensional critical statistical mechanical model, for which he received the Clay Research Award. Today he will talk about the conformal invariance and universality in the two-dimensional Ising model.
Well, thanks very much for the introduction. And it's very nice being here, and the subject which I will talk about is quite close to one of the main specialities of Australian mathematics, where people from Australia has changed a lot. And I will talk about a different viewpoint on that subject. So it's a bit, before I say what do I mean by conformal invariance and universality, I want to say a bit about what is the Ising model. And in a sense, the topic of this talk is wider. It concerns itself with a great variety of two-dimensional models. So we come to definitions in a few moments, but one should think about random counting of a lattice like one in this picture. And there are, with certain simple rules, again we'll come to this in a few minutes, and there are two-dimensional models which fairly well, in a qualitative sort of sense, model phase transitions we see in nature. And it's really amazing that you can come up with a very simple set of rules, and then you see a model where you change a parameter and suddenly at one critical value the model completely changes its behavior. So the other thing why we're interested in these models is that they are connected to field theory, and it's one of the main or most successful mechanisms of constructing rigorously field theories. So in the two dimensions, you would construct two-dimensional field theories, so they will usually turn out to be conformally invariant. And the last thing is that two dimensions, you can say much more about the phase transitions. So normally, if you consider models like the ones I'm about to discuss, in dimension 1 you won't see any phase transitions, but qualitatively you will see the same pictures in dimensions 2, 3, and usually then again it becomes trivial from starting from some very high dimension. But whereas in dimension 3 there are very few results besides results saying that you should observe a phase transition, in dimension 2 people were able to make first physically and then mathematically some very exact predictions. So I've written here names of some of the physicists who made predictions using various aspects of conformal field theory, and listed 3 of them. So one is for a model called percolation. So there, if you take different density of vertices, there is a critical density. So it turns out that if you go a little bit of critical, the average cardinality of connected cluster you would see would behave like a fractional power of deviation from the critical temperature, and a very non-trivial power at that, 43/18. So this we can now prove, at least for some percolation models. And there are many other funny predictions like that. So the first one we can now prove, the second one we are now able to prove. It's just a matter of sort of doing the technicalities. And the third one we now understand how one could possibly prove it, but it's still very far from completion. And again, it's sort of, so this one is due to Bernard-Niemhaus, says that if you take a square lattice or any other lattice in that, and you take, and you count how many lengths n walks from the origin you can have. So in square lattice it will be 4 to the power n if you count all walks. But now you count only the simple ones. This was proposed originally as a method to model polymer molecules in chemistry, positions of polymer molecules. So his prediction says that the first, it's very easy to prove mathematically that the asymptoticness of number will grow exponentially. It will be mu to the power n, where mu will depend on the length. It's not difficult to show. But it knows that the next term is a universal. It's independent of lattice, and again you see some rational non-trivial exponents, n to the power 11/32. So for a very long time, there was a multitude of predictions like that, using various methods from physics. So there were exact predictions, but there were no rigorous proofs, and really this was puzzling mathematicians. So recently, there was some mathematical breakthrough, and in a sense it does not explain one of the physics methods, but it follows the same ideology. There is a two-step ideology, and the first step that instead of looking at the discrete model, you look at what is called continuum limit. So you can say that you look at this lattice picture, but from very, very far away. So you set the microscopic size, the size of the atoms or interacting particles, to 0, and you get some random covering of the plane or something like that. And you discover that this random covering of a plane is universal. So you can try the same model on different lattices, but you will always see the same limit. And moreover, it is conformally invariant. So here comes a link with complex analysis, which is not existent in 3 dimensions, and which allows us to make such wonderful predictions in 2D. And then, well, more I will say about it later. And then the part B, that if you have an object which is conformally invariant, it puts a lot of restrictions on it. So in dimension 2, in dimension 2 only, there are very, very many conformal transformations. You know by Riemann uniformization theorem that any bounded simply connected domain can be mapped onto a unit disk. So if you have a random covering of a plane so that you cut any piece and you map it to unit disk, you always see the same. It puts quite a restriction on this random covering of a plane. It turns out that essentially there would be only one parameter family of such coverings. So physicists would say that it's a one parameter family of conformal field theories. So in mathematics, Adam Schramm proposed some more geometric and down-earth approach to it. So he constructed a one parameter family of random curves, which he calls SLE kappa. SLE stands for stochastic linear evolution, because they developed dynamically by solving certain ordinary differential equation. And for these curves, you can see that they are, with some very simple axiomatics, they are only possible conformally invariant curves, and there is parameter kappa. So if you show that some lattice model has a limit, you have only to and limit is conformally invariant, and there are some curves in this model, they will have to converge these curves of Schramm. And once you determine kappa, you can do some computations. So you can arrive at these exponents, and we'll see later how this is done. So this part, how to do computations, is understood rather well nowadays, so I will just briefly touch upon that, and it's done using the so-called intercouplings. And so the part B we sort of explain now mathematically. So the question which is still puzzling for mathematicians is why would you have part A? So I will concentrate on this question. And first I will start with a very classical example of conformal invariance, so that dates back 60 years ago to work of Paul Levy. So there is a simple model, random walk, which converges to Brownian motion. So it dates back to the work of Einstein, who probably the first to discuss at some level of mathematical rigor that random walk should converge to Brownian motion. But basically, well, you take a picture like the picture above, where a person walks on a square lattice, and at every juncture he turns with equal probability 1/4 to every of the 4 possible directions. And then what you do, you take some trajectory. So here it's of the length probably about 5,000 steps, and then you set the step of the lattice to 0. So this random broken line converges to a random continuous curve, which is called linear process or Brownian motion. What Paul Levy has shown, that this curve is conformally invariant. So if you map it conformally, so here it's mapped conformally by exponential transformation, essentially you would see a very similar curve, even in the discrete setting, if the mesh of the lattice is small enough. So you see that there are regions where mesh of the lattice is quite big. So you, for example, about here, you don't, well, you still see the directions of the lattice, so it's not conformally invariant, but in the region like this, where the mesh of the lattice is small enough, you don't really see quality difference between these two curves. So the Levy theorem says that if you forget about parameterization by time, you get the same random curve before and after the conformal transformation. So this is a very classical theorem, and we expect that the similar theorem would be true in most two-dimensional models at critical temperatures. Only it will be slightly more difficult because here there is this Markov property. You just draw a curve without looking at your past. You only take into account where you are. Whereas in most two-dimensional lattice models, you have to look at your neighborhood. So it's a bit more difficult. So here is a more recent example. So this is the model which is called critical recollection. Here it's done with hexagonal lattice because for the time being that's the only lattice where we can do it. So it becomes the simplest model to describe. Again, for every hexagon you just toss a coin. There is no interaction whatsoever. So if the coin comes up heads, you cover it yellow. If it comes up tails, you cover it blue. And you think of it as a model of some porous medium. So say there is a yellow rock, and you ask what is the chance that the water will seep through. So for example, in the picture above, is there a way to go from top to bottom using blue hexagons? So I think if you look carefully, you will see that there is a yellow path which goes left to right. So there is enough yellow obstruction for the water to seep through. Now if you take, if you want to have some physically realistic system, we should have the size of these hexagons, the size of the molecules, to be much smaller than the size of the rock. So let's take it 10 times smaller, or not even 10, 3 times smaller, and it's already very hard to see whether the water can seep through or not. And the reason is that if it can seep through, the trajectory will be a fractal curve of some fractional dimension. So what it means in the discrete setting, that to walk distance n, you have to make n to some power bigger than 1 step. So in this particular case, n to the power 7/4. So if the water can go through, it will actually go not along some straight line, but along a very curvy path. So that's the reason why it's very difficult to see. So when mathematicians start discussing this, and it started with Leibniz, Pouillet, and Saint-Aubin doing a lot of computer experiments, this got pieces to return to this problem, and John Carter just made a prediction. John Carter was a physicist for the exact value of this probability. So it's written there, so it's a hypergeometric function of the conformal modulus of the rectangle, and it looks a bit scary as it is written here, but in a sense it's less scary when you see the proof, because what he proves that if you change if you do it not in a square like here, but in a rectangle, and you change the modulus of a rectangle, then the function satisfies some very simple differential equation. But it's a non-integrable, and its solution is called hypergeometric function, so that's one of the possible definitions of hypergeometric function. So this was proved, but again in a way different from the original physics argument. So we were instead obtaining some equation not for a real parameter, but for a complex parameter. And this implied that the interfaces in percolation, the boundaries which separate blue and yellow hexagons, converge to the Schramm curves, and this allowed in turn to prove things like 91/48 written here. So I will speak about more recent results about the Ising problem, and I just wanted to make a short overview, saying that indeed there are not so many models where we were able to do conformal invariance. So there is this very classical example I mentioned of Brownian motion. So there is percolation with hexagonal lattice, and then there are random electrical networks, or also they're called uniform spanning trees. So this was done by Lowler, Schramm, and Werner in 2003. And then there is a model which is, well, there is an artificial model which is called harmonic explorer, and then there is some discretization of what physicists call bosonic free field, mathematicians call sometimes Gaussian free field, and this was done by Schramm Sheffield, but it's not exactly in the framework we are speaking about of these models of couplings. And then there are two variations of the Ising model, and Fortin-Kessler Ising model. And it's conjectured for many other models, so perhaps the most outstanding are Potts models and percolation on other lattices and self-awarding polymers, which I mentioned. So the tricky part is that if you take a conformal map of a lattice, you don't get a lattice, you get a curved lattice. So if you want to really show conformal invariance, you have to show some sort of universality. You have to show that no matter whether you take a lattice or a curved lattice, you still have the same scaling limit. So, and the chance of success lies with the fact that locally conformal transformation is just a rotation and a stretch. So, in principle, you expect that in most cases that if there is a scaling limit, it has to be conformally invariant, though there are counterexamples. So now I have to define the Ising model, and this is perhaps the first example, mathematical example of a phase transition and the archetypical example of phase transition. So here there is a picture at 3 different temperatures, at the critical temperature, supercritical, and subcritical. So you cover the plane in 2 colors, so this is lattice size, so I have 3 rectangles of the size approximately 100 by 200. And the 2 colors, blue and red, they correspond to small magnets, if you wish. And you assume that 2 nearby magnets want to be of the same color. So this would be antiferromagnetic model, or if you change x to be smaller than 1 or bigger than 1, then they will try to be of the opposite color. So what you can do, so here there is an assumption that there is, well, in real life, if you look at a piece of iron, you would see more or less the same picture, but you would have such a nice lattice structure. And also you have interaction not only between nearby molecules, but between molecules far away. But it decays fairly fast. So in some sense, just assuming that there is interaction between only nearby squares should work well. And it does work well. Qualitatively, you have the same picture as you would have in real life. Now, there is this parameter x, and the weight of a configuration is x to the power number of nearby magnets which are of opposite color. Or if you just draw all the interfaces which separate red from blue, it's x to the power length of these loop interfaces. So in these 3 pictures, I took the boundary conditions which are blue above the equator and red below the equator. And if you take such boundary conditions, you are forced to have one long interface which runs left to right. Now what happens if x is very small? Well, if x is 0, you have 0 to the power length of loops. So you can't have any loops. Once you have one loop, you are punished by a factor of 0, so this configuration is very improbable. But we have to have one interface running left to right. So what the picture tries to do for small x, it tries to minimize the length of this interface. So you get almost a straight line with very small deviations. And if x is on the opposite, very close to 1, you get 1 to some power, so it's always 1, so all configurations are equally level. So when x is 1, you get totally chaotic picture on the left. When x is 0, you get sort of order on the right. And the miraculous thing is that there is a sharp phase transition. There is a specific value of xc which was famously determined by PRIMA2009 pioneer. So it's 1 over 1 plus square root of 2. So that you always have chaos before that and always have order after that. And you have some non-trivial fractal picture in exactly this way. So this is the example of phase transition, and well, the model actually was introduced by the advisor of Ising by Lenz, and it's called Ising model because Ising proved in his PhD thesis that in dimension 1 it doesn't have a phase transition, and made the remark that in dimensions 2 and 3 it shouldn't have phase transition because his method should also apply. And the interesting story is that, which is forgotten by now, that for 15 years people thought that this is the case. And very smart people like Heisenberg and Dirac were introducing new models saying that Ising has shown that there is no phase transition. So there must be a different reason for having ferromagnetism in nature. So for example, Dirac proposed that electrons should hop between different atoms to create ferromagnets. So actually people believed him for a while. Then it was proved by Paris sometime later that this is not the case, there is a phase transition and this model works well enough. Okay. So this is a short disclaimer slide. It's for the physicist in the audience, because if there is a physicist, usually I get a remark that everyone knows that Ising model is conformally invariant because it's written in many textbooks. So it's interesting that there was no mathematical proof up to recently, and there are not really convincing physics arguments. So the most convincing physics argument is that if you assume that it's conformally invariant, then you can make predictions which agree with the numerics. So if you want to argue about that, we can do it at the end of the talk. But indeed, it's sort of assumed in physics literature to be conformally invariant, because if you make this assumption, it works very well. But there are counterexamples to that. There are models which are similar, which are not conformally invariant. So it's a bit more subtle than that. So the theorem I will be speaking about is that a critical temperature Ising model has a conformally invariant limit, and the interfaces in the Ising model, they converge to Schramm's curves. So there are two different representations for which this works, and there are two different Schramm's curves, so I will speak only about this more classical spin representation. So to get Schramm's curve, we need to make what is called evolutionary boundary conditions, like the ones on this big picture with phase transition. So you take half of the boundary plus spin, half of the boundary minus spin, and then it enforces having one interface like here, and this interface will converge to a Schramm's curve. So what I mean that if you fix the domain and you superimpose lattice, you get a random broken line. And if the mesh of the lattice is set to 0, this random broken line will converge in probability to a random continuous curve, which is given by Schramm as a solution to some random evolutionary problem. And in principle, there is a stronger thing saying that you can describe not only this interface but all the loops by some variations of the Schramm's curve, but that I'm not going to discuss. So originally this theory was only for the square graph, but we were able to generalize it with Dimitri recently to a large family of graphs, essentially for all the rhombic tilings like the one on this picture. And it's probably the biggest class where you can hope to have universality, because this interaction force X, if you have a skewed graph, it will depend on the edge. And this seems to be the biggest family of graphs where there is some reasonable definition of how you take X as a function of the edge. But again, I won't speak very much about that. And the other thing which I mentioned, that for C smaller than CC, so for this picture on the right, this interface converges to the straight line, so this has been known for quite some time, so this is the theorem of Pfister-Bellenik, but it's a completely different part of statistical physics, so it's sort of a different ideology and different tools. So using Ising as an example, I will try to sort of highlight two things and present two ideas. And the first idea is that how you extract one bit of information which is conformally invariant. So how you observe something conformally invariant in this model. The second bit is if you have observed something conformally invariant, then how on basis of this you can continue and find many more conformally invariant things. It turns out that if you have just one conformally invariant thing, then basically you can have everything. So if you put your foot into the door, then you can walk in and put many more things. So there are other things which I'm not going many other interesting things I'm not going to discuss. So the part A. So we want to find something in the discrete setting which in the limit will be a conformal invariant. So there are many conformally invariant objects in complex analysis. There are various capacities, extreme length, and most of them, they were discretized at one point to another. I and my colleagues, we have tried to apply many of those notions here, but it seems that the best chance for success, and it's so far the only thing which worked, is working with some discrete harmonic or discrete analytic, or sometimes it's maybe more correct to call them discrete homomorphic functions. So you take some function which satisfies discrete equivalent of harmonicity or homomorphicity, and which solves certain boundary value problem. And this, if it has a limit, will be conformally invariant, because in the limit it will be an analytic function which solves a boundary value problem. And then there is a distinction between what kind of boundary value problems you can use. So at first, Dirichlet Neumann were used because those are clearly discretized. Dirichlet problem just say that f of the boundary is equal to something. And Neumann is slightly more difficult. You have to say what is the normal derivative. But it seems that the future lies with the Riemann-Hilbert boundary value problems, where there is a wider choice and it leads to more interesting structures. So you have rather forms than functions, so things of the type f of z dz to some fractional power alpha. And very interesting question is whether it has any connection with random matrices, because Riemann-Hilbert problems, they were very successful in the random matrix theory recently, and here in this area there are quite a few superficial similarities with random matrix theory, so sooner or later someone should make a direct connection. So what is a discrete analytic function? So unfortunately there is no canonical discretization. So there are several discretizations which work out nicely, well, some people have favored discretization. I look at it more in a utilitarian sort of way. So if for some model we observe some relations, then we'll work with this discretization. I can say that I have a favorite one. But this may be the most widely studied discretization of the square lattice. So you start with a complex valued function which is defined at vertices. And we want to discretize the Cauchy-Riemann equation. So Cascading equation says that derivative in some direction alpha multiplied by I is just derivative in the direction I alpha, which is alpha rotated by 90 degrees. Simple as that. So what stands in for the derivatives on the lattice? Just differences. So you ask that the difference along the blue diagonal is I times difference along the red diagonal, and it's as simple as that. So most people have seen discrete harmonic functions. Then you ask that function at any given vertex is the mid-value of 4 neighbors. So it turns out that here it's very easy to prove that real part will be discrete harmonic and imaginary part will be discrete harmonic. And if you have simply connected domain with harmonic function, then there is a harmonic conjugate. And so on and so on, and all the linear complex analysis is very, very easy to reconstruct. So I listed a few things, and it makes for a very nice term paper for an undergraduate student because it's not so difficult to write, but you cannot Google it on the internet, so he has to do it by himself. But there is a problem. So you can do everything linear, but once you have to multiply things, it doesn't work. So the problem is that a product of two discrete analytic functions is no longer discrete analytic. So you can easily check that, for example, restrictions of constant function z and function z squared to the square lattice are discrete analytic. But z cube is no longer discrete analytic. There is a small error term. So this ruins the last 80% of an analysis book, because then you have to do things in an approximate sort of way, and then it becomes very lattice dependent, and that's the reason why there are no books on discrete complex analysis. So, how do you observe prehomomorphic functions in the Ising model? So, we start by forgetting about pluses and minuses. We just draw the interfaces which separate them. So we draw a picture like one above. So those curves, they separate pluses from minuses. I forgot about pluses and minuses. And then we do some interesting sort of condition. We ask for 2 points A and Z, having an interface between them. And the points are not necessarily on the boundary. One of them might be inside, or maybe even both inside. So in some sense, this picture cannot really come from the plus and minus distribution, because if point Z is inside, it cannot be visited just by the end of the interface. So it only will correspond to real Ising model when both of them on the boundary. But we will work with them inside. And if you just take this picture and you take the usual sum to the Ising model, it will be for every configuration x to the power number of edges. It's a well-known result that this will give you the correlation of 2 spins at points A and Z on a dual lattice. So if you take a dual lattice at a dual temperature, then the correlation of spins at A and Z, because A and Z are faces of our lattice and vertices of the dual lattice, will be the same. And this is what was used by Kramers and Vanier to show that the critical value has this, the critical value of the temperature is 1 over square root of 2 plus 1. So we cannot do just that, so we put in a complex weight. So we take the sum of all possible configurations like that, of the usual weight x to the power number of edges, times a complex weight. A complex weight counts how many turns our curve has made. So if it made a full turn, it's weighted by minus 1. If it made half of a full turn, the weight is minus I. So essentially you go along the curve, and each time when you turn left or turn right, you multiply either by lambda or lambda bar, where lambda is root of order 4 of minus 1. So you can arrive to the same point from different sides, and then you would have different weights. So it gives some complex number. So it's not entirely clear, if I just present it like that, why one should put in complex weights. So one reason is that if you start doing the matrix, you see you're somehow forced to do that, but there are more substantial reasons which go from physics. Maybe I'll mention some of them later. So this is the definition of a function. Now, the other way to define it, so this is a picture of Ising model where there is such an interface from A to Z. So you can think that there is a monodromy in Z. When you go around Z, plus spins become minus spins. And when you go around one more time, again, plus spins become minus spins, so you return back to your world. So you can think of this function as a statistical sum, addition function for the Ising model with monodromy in Z. So there is a square root of monodromy in Z, so which forces to have one interface ending there. So it's like you take Riemann surface of the square root and you run Ising model on it, but you ask that the two decks are negative images of each other. And so this is the picture one gets. Well, if it's too confusing, just think of that picture. But well, maybe this is physically more logical way to look at it. This is what physicists would call a vertex operator or disorder operator. So for Ising model at critical temperature, this function f of z as defined before turns out to be discrete holomorphic. It solves a Riemann boundary value problem. I'll come in a second to what that is. And if lattice mesh epsilon goes to 0, it converges to some well-defined complex analytic functions. Namely, you take square root of the derivative of the Poisson curve. So Poisson curve is just a conformal map to a half plane which maps boundary point to infinity. So it's essentially 1 over z map. So here there is this division by square root of epsilon. So if you just take this observable as it was defined, it will have a trivial limit. It will go to 0. So you have to normalize it by some order so that it has a non-zero limit. And the reason why square root pops up is because you have Riemann-Hilbert boundary values, and you have this, what physicists would call a Fermat, this spin 1/2 condition. You have this weight which somehow favors you making an even number of terms. So I want to go briefly over how one proves that this thing is discrete analytic. So actually the discrete Cauchy-Riemann relation we prove is not the one I've written, the classical one, but it's slightly stronger one, and it relates just two neighboring points. So it's you don't have to sum over 4 points, you just sum 2 points. So if you sum it around the square, then you get the classical one. So if you have, so here there is a part of square lattice. So if you have two edges u and v, and we sample your functions at the center of these edges, so you have curves which run till u or till v, then it turns out that projections of f of v and f of u on vector 1 over square root of alpha, so alpha is bisector of this angle, will coincide. Or you can write it as a linear equation in terms of f and f bar. So this is the linear equation. So it says that for every two neighboring edges there is some projection which will coincide, but it will be a different projection for different edges. So for two edges like that it will be real part of function, for two edges like this it will be imaginary part, and so on. And if you want to symmetrize it, you have to sum edges around some square, around some vertex, and then you get a symmetric form. So how one proves something like this? Well, just by finding a very simple combinatorial bijection. So the proof of this property is really very simple. So the bijection, as pictured here, you take a picture, so there are two pairs of configurations. So you take some pair on the left where the interface from A goes to the vertex V. And then you erase part from W to V and add part from W to U. Or if the part from W to V didn't exist, you add it. So you either erase it if it existed, or if it didn't exist, you add it. So if you erase these half edges from W to U and W to V, then you always have a bijection. On one side you will have a curve which ends up at V, at another side you will have a curve which ends up at U. And the left side will contribute to f of V, and the right side will contribute to f of U. And you cannot write the exact contributions unless you go all over the domain and count how many edges you have. But you can write the relative contributions because you only change your function locally. So for example, above relative contributions will be 1 and lambda. Why? Because on the left you made one more term to the left, which is weighted by lambda. And below the relative contributions will be lambda and lambda squared, because here you, if you go around this thing, then in the net what you would get, you would essentially make one left turn. And here you would make two left turns. But also there is a factor of x, because here the curve is longer. So to check that you have your condition, you have to consider all the pairs of configurations like this, and you have to check that always you have you have your equation. So our equation for this particular orientation, well, alpha, the vector alpha here is just, what is it? It's vector at the angle of 45 degrees. So it happens just to be lambda bar. So the equation is written above. And we have to plug in things like we had in the previous picture into this equation. So I plugged in two previous configurations. And this is what it reduces to. The first one reduces to lambda plus 1 being equal to 1 plus lambda. So you use that addition is commutative. And the second one reduces to something non-trivial. So you get that x is equal to lambda plus lambda bar minus 1. And this is essentially the equation which determines the value of critical temperature. So if you plug in lambda, which has argument 45 degrees, then on the right-hand side you have square root of 2 minus 1, which is the critical temperature. So this gives you another proof that this is the critical temperature. And if the temperature is off critical, you don't get the d bar f is equal to 0. You get a massive version of that. You get the d bar of f is equal to f bar times deviation from the critical temperature. So this is the discrete analyticity. So it's indeed as easy as that. You just do some combinatorial bijections. But the interesting thing is how to prove that it converges to something and how to get the boundary conditions. So the boundary conditions are also easy because if you arrive to a interior point with making some number of terms, unknown number of terms, to boundary point you can only make a specific number of terms, the same number of terms the boundary makes. Because if you try to make more terms, you just go overboard. So the winding of your curve is the same as the winding of the boundary. And since you had this power 1/2, it's essentially the square root of the tangent vector. So the problem we get is that the imaginary part of f times the tangent to the power 1/2 is equal to 0. So this is what's called Riemann boundary value problem. If it's not homogeneous, if you put something on the right, it's called Riemann-Hilbert boundary value problem. And now one has to do convergence. This is the most technically difficult part. And what is done is you take integral of the square of this function. So if this function is related to square root of tangent vector, its square is related to the tangent vector. And once you integrate, it turns out that you end up with the Dirichlet boundary value problem. And you get the Poisson curve. So you get the Dirichlet boundary value problem that the function is 0 everywhere and blows up at point A. And then to get back to f, you have to differentiate, it takes square root. And the problem is that in discrete case, f square is no longer analytic, so we cannot just integrate f square like that. So this is where the fun part comes in, and that is what I'm not going to speak about. Now, I promised to say a few words, so let me fast forward a little bit. Maybe this is, since the original idea actually comes from Australia, so I will say a few words before I say about it. So, why on earth do we consider complex weights? So it has to do, it's not so immediate for Ising model, but there are other models where there is a weight per cycle. So in Ising model, cycles all have weight 1, you don't count the number of cycles. But in other models, you count number of cycles with weight n. And Baxter had this idea that if you have cycles with weight n, you orient them. But instead of putting weight n 1/2 oriented cycle, you put a complex weight mu and mu bar, so that mu plus mu bar is equal to n. And this weight, you can write as a weight, as a product of weights of all the terms, so that every left term gives you part of this mu, every right term gives you part of this mu bar, and in the end you get mu. So every left term gives root of mu, every right term root of mu bar. So this is the reason why in other models people were considering complex weights, because then instead of counting cycles, you can reduce it to counting something local. But it turns out that also it works very well for the Ising model, that it actually more logical to consider complex weights. Okay. Now, the second part I promised to speak about is the Schramm-Loewner revolution. And here it's, I feel a bit not at ease because it's a non-trivial thing, so 5 minutes are not enough. But on the other hand, if I and my colleagues spend 5 minutes each at their talks, then eventually everyone will learn it. So I will spend 5 minutes nevertheless. So it was developed by Loewner for a completely different problem. And he wanted to do some variational calculus for domains. So he wrote a differential equation which describes how conformal map to domain changes when you draw a slit. So imagine half plane, well, you can do it in any domain, but imagine half plane with a slit which is parameterized by time t. So let's say that at time t you have slit gamma from gamma 0 t, and let's uniformize our domain. So we have half plane minus slit, and the map GT opens up the slit and sends it to half plane. Then there are, you should normalize it somehow. So the mapping is unique up to 3 real parameters. So the way it is normalized, and the tip goes to 0, infinity goes to infinity, and derivative at infinity is equal to 1. So the theorem which Loebner proved is this map with this normalization satisfies a very simple differential equation. So the differential equation is written in blue, and it has only one parameter, w of t, which is the first coefficient of expansion of our map at infinity. So if you expand our map at infinity, expansion starts like z, because we ask that infinity is preserved and derivative is 1. Then there is a known coefficient w of t. Then the next coefficient is 2t over z. So this is, normally you should put capacity, electrostatic capacity of this interval over z, but Loebner changes time so that at time t capacity is equal to twice t. And then there are some unknowns. So it turns out that if you just know the first coefficient, how it changes, you can solve the blue equation and you get a conformal map. So to track the evolution of the conformal map, it's enough to track the evolution of the first coefficient. Well, maybe it's not so surprising, because you can think that you drive a car with a constant speed of 55 hyperbolic miles per hour in hyperbolic geometry, and then you turn your steering wheel. If at every time you know how fast you turn the steering wheel, you can plot the trajectory of your car. So what Schramm suggested is to take a random w of t. And then, of course, if you take random wt, you get a random curve. So it turns out that if you take a Brownian motion with speed kappa, you get a very interesting random curve. So I will just show how one, well, idea of how one proves that in the Ising model you get such a curve. So you assume, well, or you prove for Ising model that there is a some subsequential limit, and you want to prove that it's one of the Schramm's curve. So what you do, you describe it by Loebner evolution with unknown wt. Wt is random function, unknown random function, and you want to show that this unknown random function is a Brownian motion. So how do you prove that the unknown random function is Brownian motion? Well, you prove that wt has expectations of increments of wt are 0, and expectation of increments of wt squared minus 3t is also 0. So you prove that these two things, they are what probabilistic converting case. And Levy's theorem says that it's enough to conclude that this is a Brownian motion with speed 3. So how do you get this? Well, let's look at our function, f, which is the some so to say, probability of having a curve from A to Z. So probability of having a curve from A to Z in half plane will be the same as expectation of probability of having a curve from gamma t to z in a plane with a slit, because our curve starts like this slit. So this is just the total probability formula. Now we proved that this f converges to the derivative of Poisson kernel to power 1/2. So here I took the power sigma just to show that if you change the power you can get different values of coupling Schramm-Loebner evolution. So what's the Poisson kernel in half plane? It's just minus 1 over z. So you take derivative of minus 1 over z to the power sigma, it's 1 over z to the power 2 sigma. On the right hand side it's slightly more difficult, because you have to write Poisson kernel with a plane with a slit. But you map it by gt to half plane, and there it's 1 over z. So it's 1 over gt derivative to the power sigma. Now gt, I don't want to speak of gt because gt solves some very nonlinear equation, but gt has a very nice expansion at infinity. So I plug in here as a form of power series, but you actually can show that it's a real power series expansion at infinity. And if you plug in, you can write the first 3 terms. And the first term will be the same as on the left, but the next 2 are non-trivial. On the left they are trivial. So the ones on the right should also be non-trivial. And the green one is just expectation of wt times something. Times expectation of wt squared minus 6t over 2 sigma plus 1. And this is just an easy exercise with the form of power series. So the conclusion is that the yellow thing and the blue thing, they have 0 expectations. And that's enough to conclude that wt is a Brownian motion. So indeed, it's as easy as that. It's a calculation with formal power series. Of course, there are some technicalities on top of that, but more or less this is the idea why Schramm decided to plug in Brownian motion into the low-level evolution. So somehow to finish this up, maybe I want to show a few pictures of the models where we know converges to SLE. So there is this SLE for the Ising model, it's kappa equals 3, and then the bigger the kappa, the more fractal the curve is. So I mentioned SLE for the FK Ising with kappa 16 over 3, so there I don't picture clusters because then picture gets a bit messy. And this is the curve. It's actually a curve which is not simple, it can bump into itself, but it cannot go through. Then for percolation you get even more fractal curve, and for uniform spanning tree you get a space filling curve. So you get a curve which has dimension 2, it's like a random piano curve, random conformal invariant piano curve. And there are many models which are still open, so the two outstanding ones are bond percolation and square length. It should give the same curve as hexagonal length, but we don't know, and the self-avoiding polymers I mentioned. So I think I will finish here. Questions?
I have a question.
Yeah.
So I don't get the relevance of this discrete homologic Cauchy manipulating in the general context of your talk.
Can you speak a little bit louder, please?
So what is the relevance of this discrete Cauchy manipulation in the context of, in the broader context of your talk?
What is the role of the discrete Cauchy-Riemann equation?
Yeah.
Ah, well, okay. The role is that you want you have a model and you want to show that it has a scaling limit which is conformally invariant. So what is a scaling limit is fairly easy to see for the Brownian motion and random walk. But if I give you a random covering of a plane like Ising model, it's not trivial to set up the thing. So you ask, what is a random covering of a plane? Is it random measurable covering or something else? Or should you just discuss the crossing probabilities for percolation or limits of the interfaces like Schramm suggested? So before we do all of this, we just want to show that some parameter, like probability of a crossing or correlation of two spins, has a limit. So we take some parameters which are functions of point and side. And we want to show that this function has a conformally invariant limit. So what we show that in discrete setting is it satisfies some discretization of Cauchy-Riemann equations. And then when mesh is set to 0, its limit satisfies Cauchy-Riemann equations, and so is analytic. And analytic functions are conformally invariant if you prescribe given boundary data. Maybe the more classical example, if you take harmonic functions with given boundary values, they will be conformally invariant. So this is what actually happens in uniform spanning tree. There you have or for random walk, there you have just distant harmonic functions. But unfortunately, so for random walk and uniform spanning tree, you can work with harmonic functions. For other models, as far as I know, you cannot. You have to go analytic.
You mentioned during the talk that you have some examples of critical points that aren't conformally invariant.
Well, okay, so it's a good question. So so John Cardy, well, it depends in which category. You can make enough axioms so that this will probably force everything to be conformally invariant. But John Cardy, he has a paper where he has some example motivated by elasticity theory, where it's scale invariant but not conformal invariant. So I can look up the reference for you. So there are artificial examples. And moreover, there are things which seem to be related to discrete harmonic functions which are not conformally invariant. So maybe the most well-known example is diffusion limited aggregation, where you take points on the lattice, take aggregate of points on the lattice, and then you send from infinity points by Brownian motion until they stick to this aggregate. So it's a limit for aggregation of dust on the Teflon surfaces of diesel engines. And it has discrete harmonic functions built in because you send everything by discrete Brownian motion or discrete random walk. but the current understanding, there is no mathematical proof, but the current physical and mathematical understanding is that the limit is not conformally invariant. So the limit still sees the Radi structure. If you do it on hex lattice or square lattice, it will be different. So it's actually a subtle question. I cannot say that we understand it very well. And as I said, that for the Ising model, it's so there are a couple of physics arguments which actually make sense. But if you look carefully at most of the arguments, there is some ansatz in the way which is not exactly true. So,
you mentioned in the beginning, and on the title, I guess, universality.
Yes.
Now, among physicists, we believe that all kinds of Ising models are universal, while the class you gave is probably something like all the planar Ising models or something very close to that. Is there any chance that you could, that this proof or that the proof for universality could be extended to non-planar Ising models or more general?
Well, so universality we have is a large class of graphs for Ising model with nearest neighbor interactions. As I said, it's somehow not surprising that nearest neighbor interaction gives you a qualitatively good picture. So we did not do other interactions. So one reason is that if you start doing interactions which are further away, then you don't have an easy connection with the Schramm-Lonely revolution. It will be more difficult to connect it to it, because then this curve which separates plus from minuses, there will be some interaction well across this curve, so it will be more difficult to do. So this is one of the reasons we didn't attack it, but in principle, at the boundary value problems also will be more difficult to solve. But that in principle seems to be something which is, if not within reach, but something which one can try to think about. Now, if you ask tricky questions about higher dimensions, so as I said, as far as I know, in higher dimensions there are no exact predictions for natural models. So there are some artificially created where there are some exact calculations, but usually they are not rotationally invariant. So the question is whether we can learn something from this story which is applicable to higher dimension. I think about 10% of what we do, in principle, can be considered for applications to higher dimension. So conformal invariance doesn't make sense in dimension 3. But covariance by diffeomorphisms, yes, in principle it can. Now, if you try to do some evolutions, yes, you can evolve metrics in higher dimensions, and well, people prove great theories evolving metrics in higher dimensions. So, in principle, you can do this. You shouldn't do it with the conformal web like here, but also Lonely revolution you can do without a conformal web, just writing equation for the underlying metric, how it evolves. Now, can you see other discrete equations in higher dimensions? For Ising model, I don't know. But for, say, for uniform spanning tree, you would see harmonic functions in any dimension, including dimension 3. So, in Ising model, I think you won't see discrete harmonic functions. If you would see some discrete equation, it will be more complicated. It won't be for functions, it would be for some spinors. But it's not absolutely excluded. So I think that there are a few tricks here which one can try to extend to dimension 3. But one has to be very lucky for them to work. Yes, please.
You talk about the universality.
Yes.
We know that in the two-dimensional Ising model, if it's triangular Ising model, and then it's anti-ferromagnetic, and it belongs to a different class from the ferromagnetic. So in your proof, is there conditions?
So what was that you said about triangular lattice? I didn't quite hear.
Okay. So in the triangular lattice,
Yes.
if it's ferromagnetic,
Yes.
so all the coupling and anti-ferromagnetic, they belong to different universality classes.
So yes, So the question was that ferromagnetic and antiferromagnetic models, they belong to the same class on square lattice, but not on triangular lattice. So ferromagnetic model is where nearby squares try to be of the same color, and antiferromagnetic where they try to be of the different color. So on the square lattice, it's exactly the same, because what you can do, you can cover it in chessboard fashion. And then for the black chessboard squares, you reverse the spins. And then every every pair which was plus plus becomes plus minus, and every pair which was minus plus becomes minus plus. So this works on any bipartite graph, and triangular lattice is not bipartite graph. So triangular lattice is the idea. So I would think that here this proof, so as I said, it applies to antiferromagnetic Ising model on any lattice. So on square lattice it would do also ferromagnetic Ising model, because correlations can be rewritten just by this chessboard trick. So I did not try to do ferromagnetic Ising model on triangular lattice. In principle, it also supposed to fit into this picture, so one can try it. I tried, for the time being, I tried to do all other Potts models on most lattices, and so far I have failed. I have failed. But
in the square Ising model, there are also plus trick. You can also have a plus trick.
yes.
That if the three are positive, another is one of them negative. Then they will belong to another different set.
So I didn't catch. So you have placket interactions or what?
No. You have Ising model.
Yes.
The 3 bonds, we just look at square. 3 bonds are positive. This one bound negative.
Yes.
So-called plus Ising model. Then they will be like the triangular. They belong to a different.
If you reverse back at one of the edges, I didn't quite catch.
You can have 3 bonds positive. One negative. Okay.
What's the square?
Sorry? Yeah, but maybe let's do it after the talk, because I can't hear well. So
many of us believe that this appeared from the street, that the Young-Baxter integrability is some kind closely related with the non-critical extension of conformal invariance. Could you say anything that you discovered from that?
Yes, yeah. So I first have to say that I put connection to Young-Baxter with a question mark, because it's very interesting. We get some discrete homomorphicity, and we get some equation for x, for example, like I have written, which gives you critical value of x. In Young-Baxter, you also get some equation for x, and the equations have the same solution, whereas for Young-Baxter you get nonlinear, and here you have linear. So there are some more superficial similarities, but so far, in the list of the models I made, so really analyzed were uniform spanning tree on every lattice, uniform spanning tree, and Ising model. And those are exactly the 2 models for which in Young-Baxter you have 3 free parameters when you do start triangular relation. So I would really love to understand it better. Now, what you would get here of criticality, I think I briefly mentioned this. Of criticality, you would get a massive form of Cauchy-Riemann equation. So you would get something which let me think. I think it was written somewhere. Yeah, you would get an equation of this type that instead of d bar f equal to 0, things won't disappear, but you will have some remaining terms which will be linear function of f, and it will actually be f bar with some constant in front, with some imaginary constant in front. So you get you get what is called a massive field theory. So it's not fully conformally invariant, because such an equation is not conformally invariant. Because if I map it to a different domain, what happens is that the d bar, from d bar, a term will pop out, which is the derivative of the conformal map, and it won't pop out on the right. So it is conformally invariant if you consider this mass, this coefficient on the right, as a metric. So it's conformally invariant, observable plus an underlying plus massive metric is conformally invariant. So it's a very interesting question how to describe this. So we have a much ongoing project with Nick McCart trying to describe this by Schramm-Lerner revolutions, and it sort of works, but of course it's more difficult because it's not a conformally invariant state. But I think it sort of relates to what you see using Young-Baxter. So questions? Yes, please.
Maybe this is a naive question, but does the topology on the landscape matter? You try to use a Riemann surface or Ising?
Oh, it matters. You get much more interesting pictures if you do Riemann surfaces. So of course, if you talk to a physicist who is really a conformal field theorist, he won't look at the disk. He will say that the disk is trivial. Well, this is why we put point on the boundary, point inside, because otherwise it's indeed trivial. But he would sum over all possible topologies. So for me, as a complex analyst, it would be interesting to look individually at the cases. So the observables I said, they seem to work for simple things like NOI or tori. I didn't go further than that because it requires doing potential theory for Riemann surfaces, which is more difficult. But it seems a way to go and a very interesting one. So, for example, you would get things like that. You know, there are theorems that if you have a torus, topological torus, if you put conform structurally, there are two parameters, the modulus of the torus. So, broad and motion, once you start it, in epsilon seconds, it will tell you the geometry. It will see very far away, though statistically it doesn't really leave small neighborhood. It can leave, but with very small probability. So here is the same. The Ising relations in a very small neighborhood, they immediately will tell you everything about the global geometry. But it's for now it's sort of the principle. It's not something I can prove for any sort of topology, but it's a very interesting question to explore. Yes.
We should leave it at that. So let's thank Stas once again for the very